Far off the rugged coast, where Alaska and western Canada meet the northeastern Pacific Ocean, a moderate earthquake has once again drawn attention to one of North America's most formidable tectonic boundaries. During the morning of the 3rd of August, 2026, a magnitude 4.8 earthquake occurred approximately 152 miles, or about 245 kilometers, south of Heidelberg, Alaska, at a depth of roughly 9 miles, or 15 kilometers. By global standards, the earthquake was relatively modest and caused no widespread reports of significant damage. Yet its location immediately captured the interest of seismologists because it occurred within the Queen Charlotte Fairweather Fault system, an immense geological structure capable of producing some of the largest strike-slip earthquakes ever documented. Why does a moderate earthquake occurring far offshore deserve such careful attention? Why do scientists continue monitoring this remote fault with extraordinary precision decades after it unleashed one of the most powerful earthquakes in North American history? Perhaps the most important question of all is whether this latest earthquake simply reflects the fault's constant motion or serves as another reminder that one of Earth's fastest-moving plate boundaries remains fully capable of producing another major seismic event in the future. Although the Queen Charlotte Fairweather Fault receives far less public attention than California's famous San Andreas Fault, many geologists consider it equally remarkable and, in several respects, even more dynamic. Extending for nearly 560 miles, or roughly 900 kilometers, along the western margin of North America, the fault forms the boundary between the Pacific Plate and the North American Plate. Much of the system lies hidden beneath the cold waters of the northeastern Pacific, while its northern reaches continue onshore through the mountainous landscapes of southeastern Alaska. Unlike dramatic mountain building zones or volcanic arcs that visibly reshape the landscape, this fault quietly accommodates enormous amounts of horizontal motion every single year. The absence of towering volcanoes or spectacular surface expressions often allows it to escape public attention, but the geological forces operating along its length are among the most powerful anywhere on the continent. The recent earthquake serves as another reminder that Earth's tectonic plates never remain still. The Pacific Plate is continually moving toward the northwest relative to the North American Plate at a rate exceeding approximately 2 inches every year, or more than 50 millimeters annually. That rate places the Queen Charlotte Fairweather Fault among the fastest slipping transform faults on Earth. While 2 inches may appear insignificant on a ruler, the motion is relentless. Every hour, every day, and every year, the plates continue attempting to move past one another. Over decades, that seemingly small annual displacement accumulates into several feet of relative motion, while over centuries it amounts to many yards. Geological time transforms tiny annual movements into enormous tectonic displacements. Despite that constant motion, the plates do not slide smoothly past each other. Their surfaces are irregular, fractured, and locked together by friction across numerous sections of the fault. Rocks on opposite sides resist movement until the accumulating stress exceeds their strength. As plate motion continues, the surrounding crust slowly bends and stores elastic energy, much like a compressed spring. Eventually, the locked sections can no longer withstand the increasing forces. They rupture abruptly, releasing decades or even centuries of accumulated strain within seconds. That sudden release generates seismic waves that radiate outward through the crust, producing the shaking recognized as an earthquake. This repeating process, known as elastic rebound, explains why earthquakes continue occurring along transform faults even though the plates are always moving. Every major rupture releases a portion of the accumulated strain, but it never stops plate motion itself. Once an earthquake ends, tectonic forces immediately begin rebuilding stress for the next seismic cycle. The fault therefore exists in a continuous sequence of loading, rupture, and renewed loading that extends across millions of years. For scientists studying earthquake hazards, understanding that cycle is far more important than focusing on any single earthquake. A magnitude 4.8 earthquake does not necessarily indicate that a much larger earthquake is about to occur. At the same time, it certainly does not mean the fault has become safer. Moderate earthquakes are common along active transform boundaries because numerous smaller fractures and localized sections of the principal fault continually adjust to changing stress conditions. Each earthquake represents one moment within a much larger tectonic process that cannot be judged solely by the size of an individual event. Every recorded earthquake contributes valuable information. Modern seismic networks determine the earthquake's exact location, depth, fault orientation, and rupture characteristics with remarkable precision. Those measurements allow researchers to distinguish whether an earthquake occurred directly on the principal plate boundary, along an adjacent fault, or within the broader zone of crustal deformation surrounding the main fault. The data also reveal how stresses are redistributed after each event, improving long-term understanding of one of North America's most active seismic regions. The Queen Charlotte Fairweather Fault occupies a unique position among Earth's major plate boundaries because it combines exceptional length with exceptionally rapid motion. Transform faults exist in many parts of the world, including the San Andreas Fault in California and the North Anatolian Fault in Turkey, but relatively few accommodate plate motion as rapidly as the Queen Charlotte Fairweather system. That rapid movement means tectonic strain accumulates efficiently wherever friction locks portions of the fault. Yet the fault does not behave as one continuous fracture. Instead, it consists of multiple interconnected segments, each responding somewhat differently to the forces imposed by plate motion. Variations in fault geometry, crustal structure, and local stress conditions influence the way individual sections accumulate and release strain. One segment may rupture, while neighboring sections remain locked. Another may experience numerous moderate earthquakes without producing a major rupture for many decades. These differences make earthquake forecasting extraordinarily difficult despite the extensive monitoring now available. Geological maps illustrate another important characteristic of the fault. Although it is primarily classified as a transform boundary, its behavior changes from north to south. Along much of its length, horizontal strike-slip motion dominates as the Pacific plate slides northwestward relative to North America. Farther south, however, subtle changes in the orientation of plate motion introduce a compressional component. Instead of moving purely sideways, one plate begins forcing slightly beneath the other, producing localized underthrusting in addition to horizontal displacement. That transition significantly affects earthquake behavior. Strike-slip earthquakes mainly involve horizontal movement, while underthrusting introduces vertical motion capable of producing different patterns of fault rupture and, under certain circumstances, greater potential for tsunami generation. Rather than viewing the Queen Charlotte Fairweather Fault as a single uniform structure, geologists recognize it as a complex tectonic system whose characteristics evolve along its length. Historical earthquakes clearly demonstrate that complexity. Throughout the past century, different portions of the fault have produced several major earthquakes exceeding magnitude 7. Each occurred on a different section of the system, illustrating that large ruptures do not necessarily relieve stress across the entire plate boundary. Instead, various segments follow their own earthquake cycles while remaining mechanically connected within the broader tectonic framework. Among those events, one earthquake continues to define scientific understanding of the northern Queen Charlotte Fault. During the summer of 1949, a massive magnitude 8.1 earthquake ruptured approximately 310 miles, or about 500 kilometers, of the northern fault. It remains the largest instrumentally recorded strike-slip earthquake in Canadian history and one of the most powerful transform fault earthquakes ever documented anywhere in the world. Its magnitude alone tells only part of the story. Earthquakes reaching magnitude 8 require enormous fault dimensions. They cannot occur on short, isolated fractures because the amount of energy released depends on both the area of the fault that ruptures and the amount of displacement occurring during failure. In the 1949 event, rupture propagated across hundreds of kilometers of fault, allowing tremendous quantities of stored elastic energy to be released within only a few minutes. Unlike earthquakes occurring along subduction zones, where one tectonic plate dives beneath another, The 1949 earthquake primarily involved horizontal displacement between the Pacific and North American plates. Entire sections of crust shifted sideways as friction that had resisted motion for many decades finally gave way. Although much of the rupture occurred offshore, limiting direct impacts on populated areas, the earthquake demonstrated beyond doubt that the Queen Charlotte Fault possessed the dimensions and mechanical properties necessary to generate truly exceptional seismic events. Even after such an enormous release of energy, plate motion did not stop. The Pacific Plate continued advancing northwestward at more than approximately 2 inches, or over 50 millimeters, each year. That uninterrupted movement has continued ever since, gradually rebuilding tectonic stress along different portions of the fault. One question naturally follows. Has enough time passed since the 1949 earthquake for that same section of the fault to become fully reloaded? Current scientific understanding suggests the answer is no. Since the 1949 rupture, approximately 77 years have passed. At an average relative plate motion exceeding 50 millimeters annually, only about 12.5 feet, or roughly 3.8 meters, of relative displacement has accumulated across the former rupture zone. Although that represents a substantial amount of motion by everyday standards, it remains smaller than the total displacement commonly released during many magnitude 8 strike slip earthquakes. Events of that size frequently involve several meters to well over 10 meters of slip, depending upon the rupture length, fault geometry, and distribution of stress. That comparison indicates the exact rupture area responsible for the 1949 earthquake has likely not rebuilt all of the strain released during that historic event. In other words, the northern rupture segment is generally not considered fully reloaded. Yet that conclusion should never be interpreted as meaning the broader Queen Charlotte Fairweather Fault has become incapable of producing another great earthquake. Quite the opposite may be true. Because the fault extends for nearly 900 kilometers and consists of multiple independently behaving segments, different portions of the system continue accumulating strain regardless of conditions elsewhere. While one section may still be recovering from a previous rupture, another may already possess sufficient stored energy to generate a major earthquake. That segmented behavior has repeatedly appeared throughout the historical record and remains one of the defining characteristics of this remarkable tectonic boundary. Following the great magnitude 8.1 earthquake in 1949, the fault system continued generating powerful earthquakes over the following decades. In 1958, a magnitude 7.8 earthquake struck along the Fairweather segment near Lituya Bay in southeastern Alaska. Although famous for triggering the enormous landslide-generated wave that swept high above the surrounding mountainsides, the earthquake itself also demonstrated that significant tectonic strain remained distributed across other sections of the plate boundary. The fault system had not become quiet after the 1949 rupture. Instead, different segments continued releasing accumulated stress according to their own seismic cycles. Another large earthquake followed in 1970, when a magnitude 7.4 event occurred farther along the system. More recently, scientific attention intensified after the magnitude 7.8 Haida Gwaii earthquake of 2012. Unlike many previous earthquakes associated with the Queen Charlotte transform boundary, that event was dominated primarily by underthrusting rather than pure horizontal strike-slip motion. The earthquake highlighted the changing nature of the plate boundary toward its southern end, where subtle variations in plate geometry introduce compressional forces capable of producing different styles of fault movement. Just 1 year later, another significant earthquake struck near Craig, Alaska. The magnitude 7.5 event in 2013 once again confirmed that major earthquakes can occur on separate sections of the Queen Charlotte Fairweather system without requiring the entire fault to rupture simultaneously. More recently, another magnitude 7 earthquake affected the northern portion of the system during 2025, adding another reminder that this plate boundary remains one of the most seismically active anywhere along the Pacific margin. Taken together, these earthquakes reveal an important geological principle. Transform faults of this scale do not behave as single, uninterrupted fractures that release all accumulated energy during one enormous event. Instead, they resemble a chain of mechanically connected segments, each responding to changing stress conditions over different timescales. Stress transferred by one earthquake may slightly influence neighboring sections, but it does not necessarily determine when or where the next major rupture will occur. Every segment possesses its own structural characteristics, frictional properties, and history of previous earthquakes, making each section unique despite belonging to the same fault system. Modern monitoring technologies have greatly improved scientists' ability to observe these subtle processes. Dense seismic networks continuously record earthquakes, ranging from imperceptibly small tremors to major seismic events. Satellite-based global positioning system measurements detect crustal movements with remarkable precision, allowing researchers to measure the relative motion of the Pacific and North American plates to within fractions of an inch or a few millimeters. These observations confirm that the fault continues accommodating more than approximately 2 inches or over 50 millimeters of relative plate motion each year, making it one of the fastest slipping transform boundaries on Earth. Even with these sophisticated instruments, however, predicting the exact timing of a future major earthquake remains beyond current scientific capability. Researchers can identify where strain is accumulating and estimate long-term seismic potential, but they cannot determine the precise day, month, or year when a locked section will finally rupture. Earthquake occurrence depends upon countless variables operating deep within the crust, including rock strength, fault roughness, fluid pressures, stress interactions, and the complex geometry of intersecting fractures. Those factors evolve continuously and remain impossible to observe directly at the depths where large earthquakes begin. That uncertainty often leads to misunderstandings whenever a moderate earthquake occurs. Some people assume a smaller earthquake has relieved enough stress to prevent a larger event, while others fear it automatically serves as a warning that a catastrophic earthquake is imminent. Scientific evidence supports neither conclusion. A magnitude 4.8 earthquake releases only a tiny fraction of the energy associated with a magnitude 8 earthquake. Because earthquake magnitude follows a logarithmic scale, each increase in magnitude represents a dramatic increase in released energy. Consequently, moderate earthquakes generally neither eliminate the long-term hazard nor reliably signal that a major rupture is about to begin. Instead, the latest earthquake should be viewed within the broader context of a fault system that has remained active for millions of years and will continue shaping the western edge of North America far into the future. The Queen Charlotte Fairweather Fault exists because the Pacific Plate and the North American Plate continue moving relative to one another, and there is no indication that this tectonic process is slowing. As long as those immense plates remain in motion, stress will continue accumulating wherever sections of the fault become locked. For communities scattered across southeastern Alaska and coastal British Columbia, that reality underscores the importance of continued earthquake monitoring, resilient infrastructure, and emergency preparedness. Although the most powerful earthquakes along this remote fault frequently occur offshore, strong shaking can still affect coastal settlements, transportation corridors, ports, and critical infrastructure. Steep mountainsides bordering narrow fords also remain susceptible to earthquake-triggered landslides, rockfalls, and localized tsunami hazards generated by slope failures, even when the principal fault movement is predominantly horizontal. The magnitude 4.8 earthquake recorded south of Heidelberg is therefore best understood not as an isolated event, but as another measurement within an ongoing geological process. It neither confirms that another great earthquake is imminent, nor suggests that the Queen Charlotte Fairweather Fault has become less dangerous. Instead, it reinforces what decades of scientific observation have consistently shown. One of Earth's fastest-moving transform plate boundaries continues accommodating relentless tectonic motion, segment by segment, earthquake by earthquake. The exact rupture responsible for the historic 1949 magnitude 8.1 earthquake may still be rebuilding the strain released more than 7 decades ago, but the fault system as a whole remains fully capable of producing another magnitude 8 class earthquake whenever conditions align along one of its major locked segments. Until that day arrives, every earthquake, including moderate events such as the one recorded this week, will continue providing scientists with valuable clues about the evolving state of one of North America's most powerful and closely watched tectonic boundaries.